Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into Section 5.3, Peterson's Solution. Joining me as always is my co-host, Sheila. Are you ready to unravel this classic solution to the critical section problem?
Absolutely, Victor. I'm excited to explore Peterson's solution with our listeners. Before we jump in, let's quickly recap what we mean by the critical section problem for those who might need a refresher.
Great idea, Sheila. The critical section problem is all about ensuring that when multiple processes or threads are trying to access shared resources, they do so in a controlled manner. We want to prevent race conditions and ensure data consistency. Now, Peterson's solution is a software-based algorithm that addresses this problem for two processes.
That's right, Victor. And it's important to note that while Peterson's solution might not be commonly used in modern operating systems, it's a fantastic learning tool. It demonstrates key concepts in process synchronization and helps us understand the challenges involved.
Absolutely. Now let's break down Peterson's solution. Imagine two neighbors, Alice and Bob, who share a community garden. They both want to water the plants, but they can't do it simultaneously without causing a mess. Peterson's solution is like a clever system they devised to coordinate their gardening efforts.
I love that analogy, Victor. In Peterson's solution, we have two processes. Let's call them P0 and P1. Each process has its own flag variable, and there's a shared turn variable. The flag indicates if a process wants to enter its critical section, and the turn variable determines whose turn it is if both want to enter.
Exactly, Sheila. When a process wants to enter its critical section, it sets its flag to true and sets the turn to the other process. Then, it waits until either the other process doesn't want to enter, its flag is false, or it's this process's turn. This waiting is done in a busy wait or spin-lock loop.
That's a key point, Victor. The busy wait aspect is one of the limitations of Peterson's solution. It can be inefficient in terms of CPU usage, but let's walk through the algorithm step by step. Can you break it down for our listeners?
Certainly. Here's how it works for process P0. It's similar for P1 with the indices swapped. 1. Set flag row to true, indicating P0 wants to enter its critical section. 2. Set turn to 1, giving P1 the chance to go first if it also wants to enter. 3. While flags is true, P1 wants to enter, and turn is 1, it's P1's turn, keep waiting. 4. Enter the critical section. 5. After finishing, set flagger to false. This ensures that only one process can be in the critical section at a time.
That's a great explanation, Victor. And it's important to note that Peterson's solution guarantees three essential properties: mutual exclusion, progress, and bounded waiting. Can you elaborate on these?
Absolutely, Sheila. Mutual exclusion means that only one process can be in the critical section at a time. Progress ensures that if no process is in the critical section and some process wants to enter, it can do so without being blocked indefinitely. Bounded waiting means that there's a limit on the number of times other processes can enter their critical sections before this process enters.
Those properties are crucial for any solution to the critical section problem. Now, Victor, let's talk about the historical context. Peterson's solution was published by Gary L. Peterson in 1981. While it's not the first solution to the critical section problem, it's considered one of the most elegant software-based solutions for two processes.
That's right, Sheila. It's a significant improvement over earlier attempts like Decker's algorithm. However, it's worth noting that Peterson's solution, like other software-based solutions, relies on the assumption of atomic reads and writes, which may not always hold true on modern multiprocessor systems.
Could you explain what you mean by atomic reads and writes, Victor? Some of our listeners might not be familiar with that term.
Of course, Sheila. Atomic reads and writes refer to operations that are completed in a single, uninterruptible step. In other words, when a process reads or writes a value, it happens all at once without any possibility of another process interfering in between. This assumption is crucial for Peterson's solution to work correctly.
Thanks for clarifying that, Victor. Now let's discuss some limitations of Peterson's solution. First, as we mentioned earlier, It uses busy waiting, which can be inefficient. Second, it's limited to just 2 processes. And finally, on modern hardware, we often need memory barriers or other hardware primitives to ensure correct operation.
Those are important considerations, Sheila. Despite these limitations, Peterson's solution remains a valuable learning tool. It demonstrates key synchronization concepts and serves as a stepping stone to understanding more complex synchronization mechanisms used in modern operating systems.
Absolutely, Victor. And for our listeners preparing for interviews, remember that while you might not be implementing Peterson's solution directly, understanding its principles can help you grasp more advanced synchronization concepts. It's also a great example to discuss when talking about the challenges of process synchronization.
Great point, Sheila. To wrap up, let's quickly recap the key points we've covered about Peterson's solution. 1. It's a software-based solution to the critical section problem for 2 processes. 2. It uses flag variables to indicate intent to enter the critical section and a turn variable to handle contention. 3. It guarantees mutual exclusion, progress, and bounded waiting. 4. While elegant, it has limitations including busy waiting and being restricted to 2 processes. 5. It's more of a theoretical tool than a practical solution in modern systems, but understanding it is valuable for grasping synchronization concepts.
Excellent summary, Victor. And remember, listeners, Peterson's solution is just one piece of the process synchronization puzzle. In our upcoming episodes, we'll explore more advanced synchronization mechanisms that build on these fundamental concepts.
That's right, Sheila. Thank you all for tuning in to today's episode of Operating Systems Crashcast. We hope you found our discussion of Peterson's solution informative and engaging. Until next time, keep exploring the fascinating world of operating systems.